Hello everyone! In this video we will continue to examine topic 7.1, discrete energy and radioactivity, and in particular we will transition from discussing emission spectra to discussing absorption spectra. So, in the previous set of videos, we fully explained the formation of emission spectra. So how do we create emission spectra? We can do this in a laboratory with that high potential difference applied to a thin gas of a variety of sorts. And we discussed how that provided evidence, significant evidence for the quantum model of the atom. How does it provide significant evidence for the quantum model of the atom? Well, that answer is the full explanation on the previous page, but the important structural thing to say about it is that if you assume a structure of the atom that looks like this, then that can directly explain the emission peaks that you see in the emission spectrum. And in fact, you can directly calculate those peaks if you know the energy levels of the atom. There's another type of spectrum to know about that also has this sort of elemental fingerprint. That is, the particular energy levels are always a function of the type of gas, and therefore you can figure out the element that is being used in what is known as absorption spectrum. Okay, and so here's what's going on with an absorption spectrum. Make sure, I will say, before I begin, you should make sure you fully understand the explanation for emission spectra before beginning to process what is going on with absorption spectra, because I'm going to heavily rely on that understanding in this explanation. So fundamentally, what's going on with absorption spectrum is that instead of, if you think of like an emission spectrum as being the bright sort of outcome of this process, as described before, an absorption spectrum is kind of the shadow of this process. And here's how it works. Take some kind of background source. So the sun, which produces a pretty continuous background spectrum, or an incandescent light bulb, something like that, gives you sort of a rainbow of colors. And you send that source through a thin gas. So that source, that light is shining through a thin gas. You can think of this in practical terms as sort of the atmosphere on the sun, or for that matter, our atmosphere. We get the same sort of effect. That light shines through that thin gas. And what happens is that the light is absorbed, that's why it's called an absorption spectrum, by the electrons in the thin gas, but only some of the light is absorbed. And in fact, what of the light is absorbed? Well, the light that is absorbed exactly corresponds in energy to the difference in the energy levels of the absorption atoms. So if you take that thin gas can only absorb light, or any electromagnetic wave, that has exactly the energy gap between, that has exactly the energy that corresponds to the energy gap between its energy levels. So what happens is that then the thin gas absorbs that energy, right? It bumps up the electron to a higher energy level, and then that energy, and then those electrons sort of fall back down and re-emit, okay? So if you look only at the thin gas, what do you see? Well, you see an emission spectrum, okay? If you look only at the thin gas, what you're seeing is that the electrons that have been sort of bumped up by the incoming continuous spectrum then fall back down and emit the emission spectrum. But if you look sort of through the thin gas, so let's say you're over here, for example, and you're looking through the thin gas at the source, then what's happening is that you're actually missing some of the light that corresponds to that energy level. This produces dark lines in the otherwise continuous spectrum. So if you have a continuous spectrum that normally would look like this, then actually what you see are these dips in that continuous spectrum that correspond exactly to the energy levels of the gas itself. So instead of seeing bright lines at those discrete energy levels, or those discrete wavelengths, you see dark lines at those discrete wavelengths. That's the absorption spectrum. If you have a continuous source shining through hydrogen in particular, then you will see absorption lines, shown here, at exactly the wavelengths that you would expect to see emission lines if you were looking directly at the gas. So again, in this setup, there are sort of two ways you can look at what's going on. One is you can look at the gas itself. If you look at the gas itself, you will see an emission spectrum. Or you can stand over here and look at that original source with that gas in front of it. Then what you will see is sort of the shadow of the gas itself on the spectrum that you see. You don't see the full spectrum. You see that there are gaps in the spectrum produced by that thin gas. That is known as the absorption spectrum. Now, you might ask yourself, if the thin gas absorbs the energy and then re-emits it, how come you see shadows? And the answer is that thin gas is re-emitting it not just in the same direction as it came in, but in all possible directions. So that thin gas is emitting light in all directions, which means if you're only looking at the source, then you see less of the light at these wavelengths than you would expect. But you don't see none. It's important to recognize this dip doesn't go all the way down. You do see some, because some of the light that is absorbed by that thin gas is in fact re-emitted in the same direction, but not most of it. And so you see these dips. These dips correspond to the absorption lines. All right, so if we want to analyze this in terms of the energy levels, then what we might do, sorry, probably should have erased that, what we might do is sort of invert our energy levels diagram here. So when that light comes in, the electrons in the hydrogen, for example, absorb only those wavelengths that correspond to the difference in the energy levels. And when they do so, you get this absorption line spectrum. This is the outcome. Notice they exactly correspond. So the emission lines of hydrogen exactly correspond to the absorption lines of hydrogen because they are due to the differences in those energy levels.